All right. Well, hello and welcome everyone to our continuing series, Energy Storage at PNNL webinars, where we're exploring a lot of the different storage technologies, different storage use cases that we feel are going to impact kind of our future decarbonization scenarios. So we're very pleased today to be joined by Dr. Srinivas Katipamula. Srinivas is a staff scientist at Pacific Northwest National Laboratory. For more than 25 years, his career is focused on research, development, and deployment of methods and tools related to building operations, automated fault detection, and diagnostics, as well as automated self-correcting controls for building systems. He has also advanced transactive controls and integration of building operations with the power grid to deliver energy efficiency and support grid reliability and resilience. Srinivas is a fellow of the American Society for Heating, Refrigeration, and Air Conditioning Engineers, ASHRAE, and the American Society of Mechanical Engineers. He's a recipient of the 2022 ASHRAE Exceptional Service Award, the 2020 Champion of Energy Efficiency Award from the American Council for Energy Efficient Economy, and the 2019 Leadership in Energy Efficiency Award from Northwest Energy Efficiency Alliance. So we're very pleased to have Srinivas talk to us today about utilizing buildings as a storage asset. And I think, as we look at, the new grid storage launchpad, part of our mission in there is to capture those use cases and how storage is going to be used. And if we as we start to look at these merging of standalone storage systems and then utilizing buildings as part of that storage asset, those buildings are, I think, 75 to 76% of the energy consumption in the US. So that marriage and being able to utilize both of those assets effectively is going to be a critical endeavor as we move forward. So with that, I would be happy to turn it over to Srinivas and looking forward to your presentation. I will note that please put your questions in the chat box as we go through. We will have time at the end that we will wrap up with your questions and then get back to that. But without any further ado, Srinivas, we'll let you take it away. Thank you.
Thank you, Vince, and hope you can hear me and also see my slides.
Yep, we're seeing both and hearing you fine. Thank you.
Okay, good morning or good afternoon, where you're joining us from. Before I get started, I want to acknowledge our sponsors, Department of Energy's Building Technologies Office, as well as the Washington State Department of Commerce through their clean energy funding. So the presentation will highlight why we need to use buildings as storage assets and also highlight potential virtual storage capacity that the buildings have. And I'll show you how to extract that capacity through some case studies from real buildings. And then note that those case studies that I'm going to be presenting are focused on commercial buildings. Although virtual storage is substantial, there are several challenges that we need to overcome to realizing the full benefit. Even if we do that, we still need real storage, both thermal and battery, to meet our grid needs or to minimize energy costs in buildings. I'll finish the presentation with some concluding remarks. So as Vince alluded to, buildings consume over 75% of all the electricity that is generated in the US. And they're responsible for almost 80% of the peak in the electric system. Electrification of buildings will further increase both consumption and peak contribution. It will also create winter peaks where they don't exist today. Also, large-scale integration of distributed renewable generation is resulting in significant changes to the grid operations and also grid conditions. And then the operational timing is also changing and is requiring additional operating reserves. Business as usual solutions to mitigate the supply-demand imbalance is not going to be cost-effective nor efficient. So use of inherent flexibility of behind-the-meter distributed energy resources to mitigate some of the supply-demand imbalance and support grid reliability will be less expensive and also a cleaner option, and can result in up to 20% reduction in peaks for short duration without significantly impacting the service levels in the buildings. There is significant opportunity for demand flexibility in buildings. For example, half of the electricity consumed in homes and commercial buildings could be controlled. However, with current infrastructure, only space, cooling, heating, and ventilation end uses are easily controlled. Note that currently space heating and water heating consume less than 10% of electricity. With electrification of buildings and addition of heat pumps for heating, that number is only going to increase significantly. Integrating non-traditional DERs, such as battery and thermal energy storage systems, electric vehicles, solar PV, and CHP systems will also be possible in the near future. So recently, PNNL concluded that building sector has significant, in the US, has significant potential, a maximum technical potential load flexibility of over 80 gigawatts. However, there are a number of challenges in realizing this flexibility, which I'll highlight next. Currently, many buildings lack the ability to transact energy services with utilities and other buildings or other entities. For example, less than 15% of the commercial buildings have building automation systems that can possibly control space, heating, cooling, and ventilation systems. Some smaller commercial buildings and homes have connected thermostats with limited control capability. Deployment of grid services is not common. Even those buildings that deploy grid services are mostly custom solutions that cannot be deployed at scale. Also, one-off custom solutions, which are common today, are not cost-effective. We need automation, turnkey, interoperability, which are keys for scalability of these deployments. Virtual batteries will not replace real batteries, but it can right-size the battery or the thermal storage system to reduce deployment costs. As noted previously, the reason we need to use buildings as storage assets is because traditional approach of supporting grid reliability will be inefficient and also expensive. When grid is fully decarbonized and buildings electrified, if we can overcome the challenges that I highlighted in the previous slide, by managing loads in commercial buildings, we can reduce the peaks as much as 20% without significantly sacrificing the service levels. In the near term, we need solutions that address current utility needs or grid services. For future, Transactive control provides a viable solution for coordinating responsive building loads to manage grid reliability. But these solutions must be tested in realistic situations, must be capable of being deployed in new and existing buildings, in single building, sets of buildings, or entire communities for them to be useful. There are a number of technologies that we have developed to enable buildings as storage assets. The first technology on the left is Intelligent Load Control, or ILC. It is an algorithm or set of actions. It essentially prioritizes controllable loads for managing building electricity consumption while managing the service levels. It is a top-down approach. That is, it manages at the whole building level and is more suited for current utility peak load management or demand response programs. The second technology is Transactive Control and Coordination, or TCC for short, which is a novel and highly innovative multi-layer agent-based distributed control approach to enable large-scale coordination of distributed energy resources. Note that we define any energy consuming or generation device as a DER. In the TCC approach, we apply transactive control theory combined with market concepts to encourage competition among control devices for commodities to collectively discover the optimum price. Now, we might be wondering why we need ILC and TCC to control the DERs to provide grid services. We're not going to use both agents simultaneously. ILC is a top-down approach, as I said. The grid services provided by managing the load at the building level. Whereas TCC is a bottom-up approach where each distributed energy resource participating in the market will establish its own flexibility. There are other differences and similarities between the two. To enable deployment of grid services at scale in buildings, we need an Internet of Things platform. We use PNNL developed open source product called Voltron, which is a distributed sensing and controls platform. There are the three primary use cases for this platform are first, building efficiency, that is to help control building system performance. Second, building grid integration, that is to support beyond demand response approaches and integration of DERs into the grid. Third, transactive control, that is to support scalable distributed control mechanism for transacting information between buildings and other external entities. So managing peak consumption can result in significant utility costs. Reductions even with current utility rates and programs are possible. ILC, or intelligent load control, has been shown to successfully reduce demand or enhance demand flexibility by using virtual storage capacity that exists in the building. I'll show you results from peak load management and real-time pricing in two real office buildings that are approximately 20,000 square feet with 11 and 10 rooftop units respectively. Roughly 16% of the commercial buildings in the US are in this size range. So therefore, the results that I'm going to share are representative of many existing small commercial buildings. As you all know, a large fraction of commercial buildings are subjected to both kilowatt hour, that is energy charge, as well as demand KW, which is demand charge. The demand charge can be significant, between 20 and 50% of the total utility cost. In most cases, the demand typically occurs for a small fraction of time during the month. Between 10 and 20% of this demand can be avoided without impacting the service levels. Deeper reductions are possible in demand, but you'll have to do some sacrifice. We demonstrated that ILC can be used on real buildings during heating, cooling, as well as swing seasons to reduce peak consumptions between 10 and 20%. We are showing in this slide, I'm showing a comparison of peak consumption on 2 consecutive days, March 14th on the left and March 15th on the right. The graph on the left shows results when we are not managing the peak. The graph on the right is when we are managing the peak on the very next day. Both graphs show electricity demand in blue on the left y-axis, and then outdoor temperature in purple on the right y-axis. Time is shown from 4 a.m. to 4 p.m. on the x-axis at the bottom. Note that outdoor temperatures are similar on both days, and the electricity demand that we're showing is a 30-minute rolling average. Because the building uses heat pumps with backup electric heat, the peak demand of 175 kW on the first day on the left was set around 7 a.m. in the morning. And note that the rest of the day, the demand never exceeded 145 kW. Also note that the duration of the peak was probably less than 15 minutes. Next day on the right, when we ran ILC to manage the building peak, and we set a target of 150, the red line, horizontal line, which and the peak on that day never exceeds the target of 150, which was also set around 7 a.m. Note that one or more of the heat pumps were curtailed at the bottom to manage that load change. Compared to the first day, the peak reduction is almost 15 or 20%. So like the heating season results, these graphs show comparison of the peak consumption on 2 consecutive days with similar outdoor temperature profiles in the cooling season. So the graph on the left shows when the results when we were not managing the peak, and on the right, the very next day when we were managing the peak. Again, we are showing results here from 6 a.m. to 5 p.m. And when ILC was managing the peak on July 12th, the electricity consumption exceeds, when ILC was not managing the peak on July 12th, the electricity consumption exceeded the target of 130, as you could see from that bubble there. When we were managing the peak on July 11th, several times during between 1 and 4 p.m., the electricity consumption reached the target value of 130 kW. And each time there were some heat pumps that were curtailed to manage that. In this case, compared to the first day, the reduction was about 10%. Curtailing, heat pumps or any distributed energy resources is one thing, or half the solution. We also have to look at the service levels. So in the next slide, I'm going to show you that. So the demand reductions that I showed in the 2 previous slides was achieved while we on the left y-axis, and zone set point in green also on the left y-axis. And then the compressor on-off status on the right side. So the normal set point for heat pump 8 is 72 degrees F, and during heating season. While we reduce this to 70 when we want to manage the load. So that's what you see in here. So you can also see that the blue line typically is between 70 and 72 degrees, which is what is established as a comfort requirement for this particular zone. Each zone can be customized to whatever requirements for that zone. This example results that I show here are for a 20,000 square foot office building that is exposed to real-time pricing. So we are replaying California ISO's hourly real-time prices on this building. The building does not have the knowledge of future prices. It only knows the past prices and the next hour's price. Therefore, the operations are only optimized for the 1 hour ahead. On the top left graph, the busy one, the x-axis is the time of day. It goes from midnight to midnight. And then the whole building consumption is shown on the primary y-axis on the left. That graph also compares consumption for 2 days. Baseline day with normal operations, that is in green. And then RTU day, when the RTUs in the building are responding to real-time pricing signal, the consumption is shown in blue. The price signal is shown in black on the secondary y-axis. Before each hour, when the price of electricity for the next hour is known, ILC computes demand flexibility, or the target consumption for that hour, which is shown in red. Note that the demand flexibility can be positive, that is increase in consumption when the prices are low, that is below the mean price, or the flexibility can be negative, decrease in consumption when the price of electricity is really high. The building is occupied between 6 a.m. and 6 p.m. Therefore, the control actions are only relevant during those periods. During unoccupied periods, we don't have any flexibility, so no control action is taken. During occupied period, ILC manages equipment in building to follow the target. The blue line, the actual consumption on the RTP day, as you can see, follows the target pretty closely. Also note that the consumption is high when the price is low and low when the price is high. The entire operation is fully automated. The graph on the top right shows or compares the outdoor temperatures for the 2 days. They're not identical, but very close. The bottom graph compares the cost. As you can see that the electricity cost for the 2 days, the RTP cost is slightly less than, but not by a whole lot. So here we are showing the same information or the same RTP test and same information. However, in this particular test, we constrained the RTU operation to not consume more than it would normally do under normal operation when the RTP price is low. So as you can see that the blue line on the top left graph, which is actual consumption during the RTP period, does not match the target in the red when the price is low, because we're basically trying to match the green line there. Again, the outdoor temperatures on the 2 days are comparable. So when the price is low, the blue line actually, or when the price is high, the blue line actually follows the target, and that's what we want. So because we constrained the RTU operation during the low price periods, there is over 30% reduction in electricity cost for the RTU day, as you can see from the bottom right side graph there. So those were two examples with ILC, and this is an example of how we do with the transactive control and coordination agent. Buildings can also be used to provide flexibility for the future rate schedule, like the transactive control schedule. TCC application has been designed for the future transactive energy use cases, although it can be deployed for current use case, for current utility programs as well. TCC was again tested in an office building with air handlers, rooftop units, connected lighting, and also distributed solar. So we'll look at the results for the second building that I listed there, 17,000 square foot with 5 rooftop units in a little bit more detail on the next slide. So this use case shows how we can make an existing rate schedule dynamic or market-based. So utilities are more concerned about the peaks at the distribution transformers and on their distribution and transmission networks. So currently utilities mitigate this by charging building owners for the demand they set during the month. However, this may or may not solve the utility problem because the building peak generally does not coincide with the utility system peak, or may not. Therefore, we took an existing rate, which includes a wholesale time of use energy charge, which has 2 periods, the high load hours and the low load hours, plus a demand charge for each building, and made it into a dynamic transactive rate. Because of time constraint, I'm not going to discuss the market clearing process. So this graph shows the actual whole building electricity consumption in blue, the predicted whole building electricity consumption in red, and the baseline, that is business as usual when you're not responding to the price signal, that's in green. And the price of electricity is shown in black there. And then the price is actually on the right y-axis. The 24-hour time on the is shown on the x-axis. Note that this is an office and warehouse building that is occupied between 3 a.m. and 3 p.m. on a weekday. The rest of the time it is unoccupied. Before the top of the hour, capacity predictions and flexibility of the whole building electricity are made and bid into the market. Based on the predictions, the market will provide the cleared price. If the capacity prediction exceeds the previously established peak for that building, the price will include both kilowatt-hour charges as well as the charge for demand. That's what you are seeing when the predictions go above 18 kW around 5 a.m. on the left graph for the first time. So when the prediction goes above 18 kW, the price goes to $4.50 per kilowatt hour. Because at that time in the morning, there isn't much flexibility in the DERs. The whole building energy continues to increase. And when the consumption increases to 30 kW, the market price is actually $9 kW, because it may be coincident with the city peak as well, or some sort of a city peak. At that point, we see some separation between the baseline in green and the actual whole building in blue. However, the building exhausts the available flexibility, so the whole building consumption continues to increase. So the price continues to be high until the consumption drops below the previously established peak. On the first day, the building established a peak of 48 kW. So for the rest of the month, if the whole building electricity peak remains below 48, the price of electricity will only include energy charges and not demand. So that's exactly what happened on the figure on the right, where the prices only go between 3.6 cents and 4.2 cents because the peak on that day never exceeded 48 kW. So I have a few slides of concluding remarks that I want to make, and then we'll open it up for questions. As I alluded to previously, there are some technical challenges or barriers that we need to overcome for widespread use of buildings as storage assets. For example, less than 18% of the commercial buildings covering roughly 40% of the area have building automation systems. Therefore, there is a need for a low-cost building automation system solution for the other 80+% buildings, which also require investments to make that happen. Most homes do not have control infrastructure as well. So they're also more challenging because of the fragmented market. So leveraging the infrastructure to support multiple value streams will help make investments cost effective. So there are other challenges. For example, we need detailed models to help planners quantify potential benefits of demand flexibility. First, development of high fidelity physical or empirical models requires some sort of a load-based testing of all HVAC systems, equipment in a controlled environment, so we can create more accurate models. Second, currently there is limited ability to control HVAC equipment, which is primarily done through changing set points, which works. However, we can do better. For example, with RTUs, more precise control and more demand flexibility can be achieved if equipment manufacturers provide ability to directly interact with the onboard controls. And then there are some policy-related challenges as well. On the policy front, utilities, unless utilities offer dynamic or transactive signals, widespread participation of distributed energy resources to support grid reliability is unlikely. However, they need data to be convinced that this is a useful thing to do. So recently initiated Building Technologies Office Connected Communities projects can provide such information to encourage public utility commissions and utilities to adopt these dynamic rates. Without incentives, widespread adoption of either thermal or battery storage is unlikely. However, these devices are critical for decarbonization of electricity generation and also electrification of buildings. And this can potentially increase the demand flexibility in buildings to 40 to 50% from the current 10 to 20%. So on the positive note, scalable market-based solutions can be deployed in commercial buildings to support electricity or electric grid reliability. And it can be done cost effectively and at a lower cost to building owners and utility. It will soon be possible to do the same in homes, at least I hope. The technologies that we have developed, ILC and the TCC and the Transactive network system technologies, can work cohesively to deliver market-based control solutions for future as well as meeting the current utility program needs. Peak reductions between 10 and 20% is possible for a number of use cases, as we have shown. And the use cases such as peak load reduction, real-time pricing, and also even forward-looking transactive control signals. And we can do that while meeting the service levels. Additional reductions beyond 20% are possible, but that would require some sacrifice in comfort. So that's all I had. Thank you very much for participating, and I'll open up for questions. Vince.
All right, thank you, Srinivas. Yeah, and I want to encourage our people on the webinar to please put your questions into the chat. We'll have a few minutes here to kind of go over those. But to get started on there, you at the end, and I appreciate you putting that challenges out there, of what it is. You had what, 18% of the current buildings have the automated systems necessary to implement this. And that, lower cost technologies that can be retrofit is one way. Are there standards efforts that are going on in parallel with this for like new construction or to do this, or is it already built into the most of the newer systems that they have that amount of necessary control?
No, the building controls are not something that the building codes actually mandate. Building codes typically mandate performance, and they don't require any type of controls to get that performance. However, in large commercial buildings where you have built up systems which are more complicated to manage, and those typically have building automation systems. And the reason why small commercial, there are a number of reasons why small commercial buildings don't deploy these. One of the things is what we call a mixed incentive, because most of the time the occupier of the building is not the owner of the building. They're basically leased, and therefore not owners typically don't install sophisticated systems to manage the DERs that are there. So that is the problem. And then the second problem is lack of awareness. People really don't know how much savings they can get. And some of these newer, talking about standards, right? Some of the newer requirements of benchmarking mandates, some cities and some states currently have, that has actually encouraged building owners to actually do better and install some building automation systems. But it'll take a while before, these things, before we make significant impact on the buildings. On homes, it is slightly different. The home market is very fragmented. There are so many different standards. and none of Google has its own, Apple has its own, Samsung has its own. And although they can speak to each other, it's hard for a home energy management system to be developed that talks to all of these, and that's what we would need.
You mentioned in your response there that a lot of times the occupants are not the owners of the building. I assume there is some risk to the building owners and I guess to occupants, with these, using the building as a controllable asset. Can you talk about some of those risks?
Yeah. So you could do it in a number of ways. The way that we do that, actually I had a backup slide. Maybe I should try to bring my slide back up so I could show that. So can you see my slides?
Yeah, we're seeing them there.
Okay. Okay. Yeah. So, there are a number of ways you could do that. In our case, we use that Voltron platform to initiate supervisory control decisions that we pass on to the building automation system or the connected thermostats or whatever devices that we have. And since it is a network device, there is a possibility that you might lose connection if you're not on the same network. And typically we're not on the same network. And the way that we do that is on the top left here. We basically exchange a heartbeat signal between Voltron platform that is initiating this, the supervisory controls and the building automation system that is receiving the supervisory control actions. And then once the heartbeat signal is lost between the two, the building automation system knows that it lost communication with the platform, and then it can put that building back to its normal state. So therefore, we don't leave that building in an event mode forever. So that's one way to mitigate that. And then we also, as I said, we have excursion. For example, I show on the top right, we have strict temperature limits, low limit and the high limit. And we typically try to maintain that between those two. And then once the temperatures exceed or go beyond that low limit or the high limit, the building automation system will release them from participating in the event. So that's another way to minimize the risk. And we also provide global overrides and local overrides, as we show at the bottom. So global override is if the building operator decides not to participate, they can override themselves. And then at this device level, each individual devices can also do the same thing through a priority override, which is a backnet concept.
Sorry, they had to get me clicked off mute there. So I did have a question. Obviously when we're dealing with the building, we have the human factors we have to. And so it was good to see that you do have some overrides. So in all these scenarios, the building occupancy still has that ability to say, we're not going to exceed a temperature level that's uncomfortable in there. So that's always still a local control of that. Is that the case? Or
yeah, absolutely. Yeah, that's what, there is a upper limit and a lower limit. And we maintain that temperature in that. And these can be customized, each zone. For example, if it is a closet or a conference room, or an office in the corner, they require different upper and lower limits. So you can customize those to whatever requirement that you have. So it is like pretty granular.
okay. So I'll switch a little bit here, but excuse me. You talked a couple times about the transactive controls, and can you expand a little bit about how that is a more viable solution? And maybe some of the details. What are we looking at spatially what can you talked about control, what we do on the campus and some others. How large can you have that Transactive?
Yeah, so I think I may have a slide that shows that. So let me, or at least to explain that. The definition of transactive energy, we use, Gridwise Architectural Council definition of transactive energy. What that is a technique for managing the generation, consumption, or flow of electric power within an electric power system through the use of economic and market-based constructs, while considering grid reliability constraints. So that's the definition of what the transactive energy system is. And transactive controls are essentially controls that use transactive signals to make decisions in addition to the conventional parameters that they have, that they need to make those control decisions. So, someone might say, we have dynamic prices such as time of use. Those are, changing prices. However, those are basically prices that go to devices. That is, it's just one way. In a transactive system, there is a feedback between price and quantity, as shown in the figure. So the top half of that figure here we show is sometimes referred to as the price discovery mechanism or the coordination function. Because every agent in the transactive energy networks must play a role in balancing electricity supply and demand, unless you are told how much quantity of electricity that I need, I can't tell you what the price is. And on the bottom, which is the on the demand side, it's opposite. Unless you tell me what the price is, I don't know how much flexibility I'm willing to exercise. If the price is high, I'm willing to exercise a large quantity. But if the price is large flexibility, if the price is low, then my flexibility is going to be low. So, that's the reason why you need the interaction or feedback between, quantity and the price to come up with an optimal price for the quantity that is needed. So that is why we think that these transactive systems are more viable solutions, because everyone participates in deciding what the price should be.
Okay. When you look at that, so like at PNNL, we've got several of the buildings set up, to be able to control and do that. Where are you seeing the biggest uptake? Is this at a campus level as people are starting to manage how all those assets to work? Or, I'm trying to think as transactive as you get to an entire distribution system. Just trying to get some sense of scale on where the work's at and where you think it needs to go.
Yeah, so, in the transactive network system, it is hierarchical. So when, hundreds of DERs or thousands of DERs participate, they all don't communicate to the same transactive node. So you can have a hierarchy of nodes that you establish. So in our experiments, in simulations, we've done, thousands of buildings with, tens of transactive nodes. But in real testing on our campus, we basically done maybe 3 levels. We have a transactive node at the building and a transactive node at the campus level, which is the distribution network, and then a campus and a transactive node at the city level, which is slightly bigger than a distribution network. So in the transactive energy application, it's possible to do this because it's hierarchical and we can break that problem into smaller problems and solve that. And that's the reason why we are able to do that. And in terms of real applications of this in real life, there are not very many of them that have actually been implemented. Most of them have been in pilots. We will be involved in a few pilots, as I said, on the connected communities that will look at some of these concepts to figure out, what scale we can actually deploy these things.
Okay, thank you. We had a question here that asked, in the infrastructure bill, are you aware of any programs that offer incentives for upgrading building automations? Is there any, automation and controls? That's not something I've tracked, but I didn't know if you've seen.
No, I don't track that either, but I know that there is a big push for at least K through 12 schools. There is significant funding available for upgrades, and part of the upgrades is controls, and that would come through. And on the grid side, I don't keep track of that either. There is significant investments that they're going to make on the distribution automation and transmission automation, I think. So there's a lot more money on the grid side than on the building side for these automated technologies to be deployed.
Okay. So we did have another question come in that asks, I think, just a little bit of clarification. We talk about buildings as storage assets, but then that does not necessarily mean that the building needs to be tied to a storage system.
Yeah. So as I highlighted in the presentation, there is virtual storage, which is the demand flexibility that inherently exists in buildings that you can extract. However, when we fully decarbonize the electric infrastructure or generation infrastructure, and then we electrify the buildings, there will be significant additional loads and then significant renewable generation, which is variable. And for that, the virtual capacity is not sufficient. So you would need both additional thermal storage or battery storage. And what we are trying to figure out is what is the right size. You can, if the storage costs nothing, obviously you could install that and you're done. However, storage doesn't. It's not inexpensive, and it is expensive. So, and we need to right size that. And there is an optimum size. And that's what we are saying. Extract the virtual storage that you have, and then supplement that with either thermal storage or battery storage or both to enhance that. And you will need both. Otherwise, I'm convinced that we will probably not succeed if our decarbonization goals and our electrification goals.
But the real opportunity by bringing them together, I guess, would be if you can take some of the functions off of a battery system and have the building utilize that, I may be able to have a smaller battery scale system, which hopefully is lower cost and more affordable to get into.
Yeah, and also as Vince, as you know, batteries have a real cycle, right? So you have a number of cycles that you can charge and discharge. Whereas virtual battery, it has unlimited thing, you can do whatever. So you want to use the virtual storage first and then go to battery storage. And both are needed. Again, I want to emphasize that, you need both in order for us to support the grid reliability in a completely decarbonized world.
I think one of the things that does come up is the bidirectionality of it. We love battery systems because they can both and send out, the electricity. And really, for the most part, we don't have that with a lot of the other aspects. Is that a true statement? Or
yeah, absolutely. The availability of the battery system is significantly different from even thermal storage or even virtual storage. Virtual storage only is one way, right? You can only, well, you can increase that, but you can't really generate anything. You can only, and thermal storage also is the same way, right? You can reduce the peak consumption by using thermal storage, whereas battery, it's a bidirectional thing. You can charge and discharge. You can do a number of grid services, and you can do that in a very fast way, whereas thermal storage and virtual storage have latency that will not be conducive to some of the fast grid services.
Okay. So we, it's been a few years since I've looked into it, but we were seeing a big uptake of thermal storage to help out, especially with HVAC in there, being able to make ice on off peak, and can that help you reduce your load? So what do you see as the potential? Can you reduce the size of HVAC and cost by implementing thermal storage? And what needs to be done to get more people to look at this technology?
Yeah. So absolutely, there are a number of benefits. You can reduce the size of the equipment if you have thermal storage system, because you don't need, well, if let's say if a building requires 100-ton cooling capacity, if you have a storage that will provide half of your cooling, then you can downsize that 100-ton chiller to a smaller one, like maybe 70 tons. So that's one benefit. And then another benefit, and the bigger benefit from thermal storage, is that you can shift the loads. You can generate ice or chilled water at night typically when the grid is not constrained, and maybe when the wind is blowing and you have excess power, and you can generate your chilled water at that time, and then use that during daytime when you actually need that, when the grid is strained. And in terms of the popularity of these, they are popular in climates and in regions where the demand charges are high. For example, in the Northeast and also in California. But they're not popular in the rest of the country, because there isn't any incentive for me to put a thermal storage system in, say, Richland, right? We pay $5 a kW, whereas in California or in Northeast, you're probably paying 20 or 25, and maybe even 30 or 40 kW, dollar per kW in Hawaii. So there, it makes absolute sense. So
we got a question on kind of the cost of thermal storage systems. Do you kind of know what current state of the art is? And then we had a question to compare that to battery cost. I can talk to the battery cost on there, but I'm not up to speed on the thermal storage.
Yeah, so the thermal storage is definitely cheaper or less expensive than a battery cost. And I don't know, I think it is about half of, for the same amount of relief that you can provide, it's probably cost half as much. I need to look at those numbers, but it is significantly less. However, as Vince, you alluded to, batteries can provide a lot more services than the thermal storage devices can. And one other thing, distinction is that the thermal storage system, especially the ice system where it's completely closed loop, have almost infinite cycles, whereas battery has a definite cycle limit, whereas you can run these thermal storage systems for 10, 20 years and still not lose much.
So yeah, like you said, we haven't developed that infinite cycle battery yet. May still be a few years away. But I think, back to the question on battery cost, we are seeing, especially I'll give lithium ion as the example, because that's predominantly what's being deployed right now. Your system's on the order, the core technology of it may be on the $150 a kilowatt hour to 175. but you have to keep in mind that you still need to balance a plant or balance a system around that. So do you have HVAC controls that are on your battery system? That has to be considered into the cost. You have the controls and communications. You have siding of that battery where you're pouring a concrete pad, and you probably have an engineering team on it. And so really by the time you get to an installed cost, that $175 a kilowatt hour is probably on the order of about $400 to $450 per kilowatt hour. And so, you know, a lot of the things we do at the lab is not only addressing the technology cost, but what can we do through standards to reduce some of the, you know, engineering, procurement, and construction costs, you know, or other systems that go into that are needed for safety. So, yeah, I think that's a good frame. And I like what you point out. We're running at the end of the time here. But, you know, in a lot of cases, we need these systems to be able to do multiple value streams. You know, we want the most flexibility we can get from these assets. And that's where being able to utilize the building, being able to use a thermal storage system in conjunction with it or a battery system really does kind of give us that ultimate flexibility that we need to respond. So,
Yeah.
All right. Well, Srinivas, thank you very much for your time and presentation. Thank you, everyone, for your questions. I think Laura put in the chat, the recording of this will be available on the website, and I think it's in the chat there. I would encourage all of you to join our next webinars coming up. So on June 23rd, David Reed will be talking about the reliability test laboratory and the work that we're doing in there. And then Sarman and Diane will be talking about energy system controls on July 14th. And then one that we're looking has received a lot of attention is hydrogen as a long duration energy storage asset. And Jamie Holliday will be talking about that on July 28th. So thank you again for your attention. Thank you for your questions. Srinivas, thank you very much for the presentation. Really appreciate it. Thank you until we'll see you in 2 weeks.